So we were talking about torque, the idea of torque, and I want to continue with this cross product here. So our torque is going to be the cross product between the radial vector and our force. So we would take our hand and point it into the direction of the radial vector, and then curl our hand towards the force, and that'll tell us the torque direction with our thumb, okay? So just like this person does, they take their right hand, they put their hand in the direction of that radial vector, and then curl it towards the force, okay? Curl their hand towards the force, and then they will point in the direction of your torque with your thumb, okay? So I just want to point that out, and it also in this diagram shows you where your perpendicular r vector is in this case. So then we want to look at an axis of rotation. Okay, if we have an axis of rotation, or we have a rotational object and with some radial vector here, with some force being applied. Okay, so this is how we would look at one of our scenarios, and we would figure out where the torque is, or what direction the torque is, and in this case it is out of the page. So again, point your fingers in that direction, curl towards the force, and you'll get the torque direction. It's not out of the page, it's saying that Z is out of the page. Sorry, I read that wrong. Okay, so let's go ahead and do one of these examples real quick. So this is 10.14. It says that this figure shows several forces acting at different locations and angles on a flywheel. We have F1 equals 20 newtons, F2 equals 30 newtons, and F3 equals 30 newtons. And our radius is 0.5 meters. We want to find the net torque on the flywheel about an axis through the center. So about this center of rotation, or axis of rotation. Okay. So our net torque is going to be the summation of each torque. Okay. So we'll have some torque 1 for the first force, torque 2, and torque 3. Okay, so let's first examine everything that's going on here. So we are looking down at this flywheel, okay? And so this is the axis of rotation, meaning that it is rotating either this way or this way, okay? Now, we can see that F1 is making some angle with the radial vector there. Okay, so T1 is going to be the radius times the force F1 times sine of its angle, which is going to be 30 degrees. Okay, that's going to be tau 1. Okay, tau 2 is going to be the same thing. We have R and then F2, and we need to figure out what angle it's making with the radius. Okay, so if I go ahead and draw another radial vector here, okay, or another radius, we can see that, whoops, it makes a right angle with the radius. Okay, so that means we have an angle of 90 degrees. Okay. All right, now let's look at the third one. So this one, we'll again draw a little guy here. This is actually in the same direction, right? Well, 180 degrees off, but still we have that these are in the same direction, in the same line. So we would have R F3 sine of 0 degrees. Okay, so that would be our tau. for the third force. And so this tau would be 0 because sine of 0 is 0. Whoops, I should have put that there. Okay, so this is 0. All right, so let's see. Our sum of torques, or our net torque, is going to be Rf1 sine 30 degrees plus Rf2 sine 90 degrees. Okay, and sine of 90 degrees is actually just 1. So we'll have our radius, which is 0.5, times our first force, which was 20 newtons, sine 30 degrees plus 0.5 times our second force, which is 30 newtons. Okay, oh, I didn't even put my unit here. This should be meters, and this should be meters. Okay, so our torque, if we plug this into our calculator, we have, let's see, 0.5 times 20 times sine of 30, and then add that to 0.5 times 30, and we get 20, and this is in Newton meters. All right, so our net torque is 20 Newton meters. Okay? All right, so let's look at Newton's second law for rotation. And I know that this is a very long lecture, and I'm sorry, there is quite a bit of information, and I'm trying to get as much as I can to you guys. Only some left, okay? I'll try not to go too in depth, but this is Newton's second law for rotation, okay? It is the summation of all of the tau, or the torques, and it equals to I alpha, okay? And this is very similar to what we see in translational motion, since F equals ma. You can see that comparison there, okay? And so we can relate torque to moment of inertia and rotational kinematics. And so this is also called the rotational dynamics equation. Okay, and in vector form, it is as so. We're just putting vectors over the tau and the alpha. Okay. All right, so I'm going to go ahead and move on. Let's see. Trying to see what will be the most valuable. We exert a force, some radius. We want to calculate angular acceleration. Okay, so yeah, we can do this one real quick. Example 10.16. I will just do the first part. I'll skip the second part. You can see that in the example on the text, in the textbook if you want. So it states that, consider the father pushing a playground merry-go-round in this figure. He exerts a force of 250 newtons at the edge of the 50 kilogram merry-go-round, which has a radius of 1.5 meters. Calculate the angular acceleration produced when no one is on the merry-go-round. So it is just the merry-go-round itself. So we want to know the angular acceleration. Okay, so we just found that torque is equal to I alpha. So torque is equal to the sum, I should say, of I alpha. Since we do only have one thing that we're looking at, we can go ahead and say that this is just going to be I times alpha. Okay. We also know that torque is equal to Rf and times sine theta. Okay. He is exactly perpendicular to pushing the merry-go-round. So sine theta in this case is going to be sine of 90 degrees. So that equals 1. Okay. All right. So alpha is going to be equal to R times F divided by I, our moment of inertia. And we looked at a merry-go-round case earlier. So I'm going to go ahead and go back to that and find what that moment of inertia, actually I can use this equation. Remember we treated it as a disk, a solid disk about a cylinder axis. So we will go ahead and use this equation again. So mr squared over 2. Oops. It's going to be over mr squared over 2. Okay. All right. So this would give us so 2f over mr. Okay, if we crossed out the r, put the 2 up top. So we'll get what? Our force is 250 newtons. Our mass is 50 kilograms, and our radius is 1.5 meters. Okay. So we have 2 times 250 divided by 50 times 1.5. And so we have 6.67, and this is it's going to be in radians per second squared. Okay, so if we wanted to do the next part, which I'm not going to do right now, but the only difference is going to be that this I is going to expand. So there's going to be more than one I there. Okay. All right. So let's go ahead and move on to the work energy theorem for rotation. And remember that the work energy theorem for a rigid body is equal to K, or the kinetic energy of the final kinetic energy minus the initial kinetic energy. So this is the work done. Okay, and so we'll use that exact same thing for rotation, except for now our kinetic energy is written differently. So our kinetic energy is now equal to 1/2 I omega squared. Okay, and so we can rewrite this as an integral as well over the sum of torques. Okay. Let's see. Trying to see what is useful. Okay, string is wrapped around the pulley in this figure. It's pulled down to constant force with this magnitude. Oops. Wait, there we go. Okay. This magnitude, the radius r, and moment inertia I of the pulley are 1.1 meters and 2.5 times 10 to the negative 3 kilogram meters squared respectively. If the string does not slip, what is the angular velocity of the pulley after 1 meter of string has unwound? So we have some force, we have a radius, and we have an inertia. Okay, we want to know what the angular velocity is. So omega of the pulley after 1 meter of string has unwound. So we want to somehow relate it back to this work energy theorem. Okay, so let's see. Work from A to B is equal to, oops, that was weird. Nope, that doesn't make sense. I think it's going to be with the kinetic energies, and we'll have to continue this in the next video, unfortunately. Sorry about that, guys. This is a pretty long one.